Hello, this podcast is on circular motion. Specifically, we're going to talk about radial and tangential components, forces of circular motion, accelerations of circular motion, uniform circular motion, and vertical circles. The first thing we need to do in analyzing circular motion or understanding it is we need to think not in terms of x and y components, but in terms of radial and tangential components. You can think of it as an informal coordinate system, like an alternative to the XY coordinate system. A unique feature of this informal coordinate system is that the coordinates move with the object. So the radial dimension is the ray from the axis of revolution, or the center of the circle, through the object. So no matter where the object is, the radial dimension will run through the object, starting at the axis of revolution. As far as directions are concerned, moving outward away from the axis of revolution is considered the positive direction, and moving inward towards the axis of revolution is considered the negative direction. The other coordinate is the tangential dimension, and it is always going to be the tangent line to the circle at the point the object is on the circular path. As far as directions are concerned, if you're moving counterclockwise on the tangent line, that is considered the positive direction, and moving clockwise on the tangent line is considered the negative direction. Now that we understand our radial and tangential components, let's take a look at the forces of circular motion. When analyzing forces, we always need to break the forces down to their radial components and their tangential components. Much like when we study linear motion, we need to break forces into their x-axis components and their y-axis components. So radial forces, net radial forces, will be along the radial dimension, and they cause the object to change direction, because they are always perpendicular to the motion of the object. And if we remember, perpendicular forces cause change in direction. In fact, we give a special name to the radial net force. We call it the centripetal force. Tangential forces cause the object to speed up or slow down, and that is because the net tangential force will either be in the direction of motion, which causes the object to speed up, or it will be in the opposite direction of motion, which will cause the object to slow down. The total force acting on the object is simply the vector addition of the net radial force and the net tangential force. Let's move on now and talk about accelerations of circular motion. And of course, through Newton's second law, the accelerations are caused by the forces. So I just brought over our total force equation from the previous slide. We can apply Newton's second law to this. We can replace the radial force with the product of mass times the radial acceleration, and we can replace the tangential force with the product mass times tangential acceleration. So the radial acceleration, also known as the centripetal acceleration, is the rate at which the object's direction changes. So again, this is not measuring how its speed or magnitude of velocity changes, but the radial acceleration is measuring how fast the direction changes. That rate of change is the tangential velocity squared divided by the radius of the circle. The tangential acceleration is the rate at which the object's speed changes, and that is equal to dv dt. The absolute value sign is here just to indicate that we're dealing with the magnitude of velocity and not the direction, because of course in circular motion the direction is constantly changing. So the tangential acceleration is equal to the rate at which the velocity's magnitude changes. The total acceleration is once again the vector sum of the radial component and tangential components of acceleration. Let's move on and look at an example. A ball is tied to a 0.5 meter string, and it's moving at 1.5 meters per second when it is at an angle 20 degrees counterclockwise from the vertical. So here is the ball tied to the string. Here's the vertical. So 20 degrees counterclockwise is its current position, and its current velocity is 1.5 meters per second. What is its radial, tangential, and total acceleration vectors? Well, first, let's look at the radial or centripetal acceleration, and the formula for that is v squared divided by r. I have a negative sign in front of this because the acceleration is acting towards the center of the circle, which is the negative direction. And so we go ahead and plug in our numbers for the velocity and the radius, and we find that the radial acceleration is negative 4.5 meters per second squared. Next, we'll look at the tangential acceleration, and this is the tangential component of the acceleration due to gravity. Let's take a look at the force diagram on the ball at its current location. We have the force of gravity acting straight down. We break that into its radial component and its tangential component. And of course, the radial component will balance the tension force in the string, and the tangential component of gravity will provide the acceleration in the tangential dimension. We know the acceleration due to gravity is negative 9.8 meters per second squared, but we need to find the portion of that that is in the tangential dimension. This angle right here is 20 degrees, and so if we take the sine of 20 degrees, that'll give us this vector arrow, which is in the same length and same direction as our tangential dimension. So the tangential acceleration is negative 3.4 meters per second squared. Lastly, we can do vector addition to come up with the total acceleration. Using our Pythagorean theorem, we come up with total acceleration of 5.6 meters per second squared. As we know, this formula will give you the magnitude of acceleration. It will not give you the directional sign. In this case, the acceleration is in the negative direction because the object is moving clockwise. Now that we've learned about the radial and tangential components of forces and accelerations and how they contribute to circular motion, let's move on and look at two special cases of circular motion. The first one is uniform circular motion, and this is defined as an object that moves in a circular path with constant speed. The only acceleration that's happening is the change in direction. The magnitude of the velocity is not changing. So that means the only net force is in the radial dimension, because that is the dimension that causes changes in direction. There is no net tangential force because that would cause a change in speed, and with uniform circular motion we're at constant speed. So in uniform circular motion, the only forces we have are known as centripetal forces, and the only acceleration we have is centripetal acceleration. So let's take a look at some sources of centripetal forces. And first we need to realize a centripetal force is not a specific force acting on an object. It is the net force acting on an object in the radial dimension. So sometimes that may just be a single force, but other times it could be a combination of forces that create that net force. And it's the net force that we call the centripetal force. Here are some sources of centripetal forces. We have friction. An example would be car tires on a road. The road creates the friction force with the car tires to provide the perpendicular or radial net force. We could have a tension that could be in a chain or a rope. An example would be playing tetherball. It is the tension force in the rope that keeps the tetherball moving in a circular path. We can have the normal force act as a source of centripetal force. This is especially true when you go around a curve that is banked, and you'll see banked curves on racetracks. And the reason for this is because not only do you have the friction force between the road and the tires causing the centripetal force, you have the radial dimension or the radial component of the normal force also adding to that total centripetal force. We have lift. An example of that would be the wings of an airplane. You'll notice that when a plane goes to turn, it has to dip its wings to the left if it wants to turn left, it needs to dip its wings to the right if it wants to turn right. By dipping its wings, the plane creates a radial component of the lift force, which acts as the centripetal force. And gravity can also be a source of centripetal force, and that is an example of satellites orbiting the Earth. It's the pull of the gravitational field that's creating the orbit. And same thing with planets orbiting the sun. It's the sun's gravitational field that's exerting the centripetal force on the planets to keep them in elliptical or near circular orbit. This list is by no means exhaustive. There are certainly other sources of centripetal force, because any force with a component in the radial direction is a source of centripetal force. Let's move on and talk about vertical circles. A vertical circle is, just as it implies, a circle that is in the vertical plane. An example of this would be a yo-yo, a Ferris wheel. They're just some of the common examples. So there are some key constant characteristics of a vertical circle. Gravity is always present. There must be another force with a radial component. Examples of this other force would be the tension in a rope or the normal force of a roller coaster track. So let's just take a look over here at this drawing, and we've identified in this case the force of gravity as well as the other force F. So the other force F always needs to be in the radial dimension or have a component in the radial dimension. So there will always be a portion of the force that is pointing towards the center of the circle, regardless of what position we're at on the circle. The gravity force, however, is a different situation. It is always acting down. So when it is at points A and C, it will be entirely in the radial dimension. When it's at points B and D, notice that the gravity force does not have any component in the radial dimension. And at other points in between these four, a portion of the gravity force, but not all of it, will be in the radial dimension. Let's look at the magnitude of the net force in the radial dimension for the different positions. When you're at position A, both forces are pointing towards the center of the circle, so the magnitude of the radial force will be F plus F sub g. Keep in mind that F could be this total other force, or it could just be the radial component of the other force. When we're at positions B and D, because gravity has no radial component at these positions, the radial force, or the net radial force, is going to just be equal to F. And at position C, the net radial force is going to be equal to the magnitude of F minus the magnitude of the gravity force. Armed with this information, let's look at some conceptual points, or important conceptual points of vertical circles. At position A, force F cannot be zero for the object to continue on a circular path, because once the object moves past point A, the radial component of gravity is going to decrease. Then there must be another force in order to keep the centripetal force constant, so the object can stay in its same circular path. So if F disappears at point A, this object would take a wider radius curve. At position C, F needs to be greater than F sub g so that there is a net radial force pointing towards the center of the circle. If F sub g is larger than F, then the net radial force is going to point in this direction, and the object will start following a curve or circular path that has some point down here as its center. As we mentioned before, at positions B and D, F sub g has no radial component. So in a vertical circle, gravity has an inconsistent contribution to the net radial force, and that causes our last important characteristic of a vertical circle. The radial component of the force F changes throughout the circular path. Since a circular path needs to have a constant radial force or a constant net radial force, if the force of gravity's contribution to that net radial force is constantly changing, then F's radial component contribution has to also change to keep the total radial force constant. So for instance, the radial force F is at a minimum at point A, and it's at a maximum at point B, because it needs to cancel out the force of gravity or offset the force of gravity plus provide the centripetal force. Whereas at point A, both the gravity force and the force F contribute to the centripetal force. At points B and D, the radial component of F is the centripetal force because, of course, it's the only force at those points acting in the radial dimension. So these are some unique aspects of vertical circles, and this wraps up the information we wanted to go over in this podcast. So let's just summarize. Think in terms of radial and tangential components when analyzing circular motion. Radial forces and radial accelerations cause changes in direction. Tangential forces and tangential accelerations cause changes in speed. Total forces and accelerations equal the vector addition of these radial and tangential components. Uniform circular motion has only radial forces and radial accelerations because the object is moving at a constant speed. It is only changing direction. Any force with a radial component can act as or contribute to the centripetal force. Vertical circles have gravity and at least one other force. And finally, the radial component of these forces, the gravity force and the other force, varies based on the position of the object on the circular path. Well, this wraps up the information we wanted to cover on circular motion. I hope you found this helpful, and have a good day.